So we are now at chapter 15 in our progression of understanding probability, and chapter 15 is aptly titled Probability Rules, and it really does. And this journey that we are on is to get towards where do random variables come from? Random as in like not just pulled out from the ether, but what do these random processes really look like? And in order to talk about random variables or sampling distributions, we need to understand the fundamentals of probability and what it means to be independent or disjoint or mutually exclusive if you want to use those words. So again, I got the problems for the homework listed for you all. And I just want you to, the objective that we are going through is students use the general addition and multiplication rules to find probabilities of random events. And we will have an addendum that will go over permutations and combinations. And as I've done a little bit of research, a lot of the college statistics courses people take do not actually teach you how to do probability. They go, that's more for math-based people, and we're not going to really focus on it. But yet all of the conclusions that we are making after this rely foundationally on understanding probabilities. And so if we don't have this solid understanding, then everything else that we do from here on out is just going to make no sense. So we first start off with this or statement of what if events are not disjoint. Oh, okay. When two events A and B are disjoint, or they don't share anything in common, we call those mutually exclusive events. We can use the addition rule for disjoint events and say that A, the probability of A or B, or union B, is just the probability of A happening plus the probability of B happening. Now, however, when the events are not disjoint, or they have something in common, like we saw before, this earlier addition rule will double count the probability of A and B both occurring. We see that this overlap gets double counted, and thus we need the general addition rule. So the general addition rule follows suit just from this example. So like say we have a deck of cards and we're asking, what's the probability of getting a 10 or a club? So in blue, we have this highlighted that we have 4 10s that we can all see. And we also see that there are 13 clubs altogether. So one would think that you take the probability of getting a 10, which is 4 out of 52, plus the probability of getting a club, which is 13 out of 52, and we just add these two. And if you say the answer is 17 out of 52, you are 1 more than you had to. And that is because this 10 of clubs is both a 10 and a club. So we have to subtract the 1 that we double counted to account for that situation. And with decks of cards, it's easy to tell you that the 10 is included in both events and we would be double counting it. So we don't want to do that. We're just counting here. So this is the general addition rule, and it says thusly, and it's on your formula sheet from the AP Stats equations that we've seen. If we are finding the probability of A or B happening, it's the probability of A plus the probability of B minus the overlap. So minus the probability of A intersect B or A and B. Okay. Still focusing on the not disjoint events or overlapped events. Suppose we have a company with 66 employees. We have 14 in maintenance, 37 in production, 8 work in the office, and 7 work in management. If one employee is chosen at random each month to get a good parking space, what's the probability that a maintenance or production worker is chosen? And this is where you have to ask yourself, is there any way we could have overlap when we are dealing with this idea of an or sentence? So could you have maintenance or production, or are those events mutually exclusive? So this is very simple if we assume the positions are mutually exclusive, meaning they share nothing in common. All we have to do is say we have 14 out of 66 plus 7 out of 66, which makes a total of 21 out of 66, or we can simplify that to be 7 out of 22. But what if a maintenance worker is the maintenance supervisor. Maybe they're in management. So then the jobs are not mutually exclusive. So we would have to subtract the double count because are they in management or are they in maintenance or are they the maintenance supervisor? And so in order to do that, we would get 14 out of 66 plus 7 out of 66. That's the same first two, minus the overlap, which gives me 20 out of 66 or 10 out of 33. And really it goes to, it depends. And here is our second time that we're seeing this notation. First time we saw it was in class, but when we looked at contingency tables, we discussed conditional probabilities and conditional distributions. And this leads us to conditional probability. So when we want the probability of an event from a conditional distribution, we write B given, this vertical line means given, A has already occurred. So the probability of B happening given we already know that A happened. So this is a huge idea in statistics, is this idea of conditional probabilities. So I'm going to look at it through a table and try to identify this a little bit clearer. But if you get lost, this is where we really need to ask questions so we can clarify this idea, because it's important in order to prove things are independent of each other. So to find the probability of the event B given event A, we restrict ourselves to only the outcomes of A happening. Okay, what does that mean? When we find the fraction of A outcomes in which B also occurred, so B given A is the same thing of the probability of A and B happening at the same time, divided by the probability of A happening. So, okay, let's be specific. What is the probability that A1 happens given B1 already happened? We know we are here. So in this case, I want you to look at what's the probability that A happened divided by, or given we're in B1. So that second part tells you the column that we are in. And I want to know where is the overlap. So the probability that A1 happens given that B1 occurred is A divided by A plus B plus C. That's that conditional distribution across the row. Okay, what's the probability that A2 happens? Let's do this in a different color. Given B2 occurred. So B2 is our secondary total, so DEF, that goes in our denominator, divided by what's the overlap between A2 and B2. So that is E in this case. What happens if we reverse this knowledge? What's the probability that B1 occurs given A1 happens? So this is now looking at the column total. So instead, I'm going to delete these two. Let's pick a different color. Let's say purple. If we're looking at the probability that, what's the chance that B1 happens given we already know A1 occurred? Well, if A1 occurred, that means all of these are valid. So we're using this row, this column subtotal as our new sample space. And then we're looking at the overlap between those two, which is A. So we can switch these orders, and instead of looking at all of the sample space, which is A plus B plus C plus D plus E plus F, we are looking at a subspace, or a subsection of those totals. This is where being able to read a contingency table really comes in handy. Also, how do you set these up? For example, let's pretend for a moment that 75% of students study at least 3 hours for a statistics test. So the probability study is 0.75. There's a 50-50 shot, or 50% of the students study at least 3 hours and do the homework. So we have the probability of study and homework is a 50-50 shot. We have the probability that they've studied is 0.75 for at least 3 hours. We know that from our conditional distribution setup, we said the probability that person studied given they did their homework would be, we want the reverse. We want to know what's the probability that they did their homework given they studied. Homework given study is, I want you to think, go to the secondary spot. That second piece of information is the probability that they studied. We know that information. The numerator would be the probability that they did their homework and studied. So in this case, our setup would be 0.5 divided by 0.75 is equal to the conditional probability that they did their homework given that they were already part of the study group, which is 2 out of 3. We'll do one more, and then we're going to take a break and come back in the next video. So again, I'm emphasizing this idea that it will be helpful for you to put your data into a contingency table. So in this picture, which we've seen earlier this year, we have mammals, birds, reptiles, amphibians. And are they native to the US or are they foreign? And so each of these totals, we can either look at how many things we have from the United States, which is 165, or we have foreign, which is 498. If we add these two totals, we get 663. We could do the exact same thing for the columns and find out how many mammals we have, or birds, or reptiles, or amphibians. And so if we go to simple probabilities, we could be asked, what's the probability that something is foreign? Well, something is foreign is 498 divided by the total number of things. Well, what's the probability that we have a bird? Again, we go to totals. Birds are 253 divided by the total, which is 663. Notice foreign and birds are not disjoint because we know that there are foreign birds in this total. Foreign and bird is 175 out of 663. So the interesting questions could be, what's the probability that it is foreign or a bird? Well, we just said 498 out of 663 are foreign. 253 out of 663 are birds. And then we have to subtract the overlap because we're double counting. Notice that with fractions, the denominator is all of the same, so we can just add the numbers on the top. So what's the probability that you are foreign or a bird? Is 576 out of 663. Lastly, if we're applying our conditional probability, again, we know probability of foreign, bird, we know foreign and bird, we know foreign or bird. What's the probability that they are foreign given they're a bird? Or what's the probability that they are a bird given they're foreign? Okay, so notice the order matters. This setup would be the probability of foreign. Let's rewrite this. Our numerator is the probability of foreign and bird divided by the probability of being a bird. 175 over 253. If we switch the order, what's the probability they're a bird given that they are foreign? We see that we have 175, which is the overlap, but instead of looking at how many birds we have, we're looking at how many foreign things we have, which is 498. So origin and animals are not independent. They're not independent because in essence, what we can say for independence, think back to the notes from chapter 14. If not, I can put them on the screen for you all. The chances, saying what's the probability that they are a foreign, given that they are a bird, is not equivalent to the probability that they are just foreign. If these two were equal, then one wouldn't depend on the other. And this idea of independence comes back again and again because it matters. So we're going to pause right here. We've got quite a number of examples looking at pictures of Venn diagrams, contingency tables, and tree diagrams for those piercing male-female students. And I will see you in part 2, Falcons.